Hello students, I am Dr. Kumar Gupta. I am assistant professor at physics department in DBS college. So in this video lecture, I am talking about the simple harmonic motion. So before discussing simple harmonic motion, we should know what is motion. So motion is the movement of any body with time. And if this motion is constrained in some condition, then we can name it accordingly. So before understanding what is simple harmonic motion, we should know what is periodic motion. So periodic motion is a motion in which the motion repeats itself after equal intervals of time. So if a particle is moving and is following some path, and then after some time it repeats itself, then the motion is called periodic motion. The example of the periodic motion can be a tuning fork, motion of a pendulum, or movement of the needle in the clock. So like in pendulum, the bob is moving from point A to point B and then point B to point C, and then it goes back to B and then A, and this motion repeats itself in a particular interval. Here in the graph you can see that the displacement is increasing with time, and then after a certain interval it is decreasing, and then following the same trend after a certain interval. That interval is called a time period. Now coming to the next motion, which is oscillatory motion. So when a motion is periodic and also it is moving to and fro about a fixed position, then this motion is called oscillatory motion. So every oscillatory motion is periodic, but every periodic motion is not oscillatory. For example, the motion of Earth around the Sun is periodic but not oscillatory because it is completing one circle around the Sun in the same time, but the motion is not to and fro. So this cannot be oscillatory. However, the motion of the pendulum is an oscillatory motion because it moves around a fixed point B here and then moves to A and then moves to C in the particular time interval. Now coming to the simple harmonic motion. The simple harmonic motion is oscillatory motion of a particle which moves back and forth about the fixed position under a restoring force, which is proportional to the displacement from that fixed position. And this force is opposite in direction of that displacement. So what does that mean? The restoring force tries to move the particle back to its original position. So that is why it is opposite to the direction of the displacement. So when this motion is linear, it is called linear simple harmonic motion, while when the motion is angular, it is angular simple harmonic motion. What is the example? So like if a body is attached to a spring, then the motion will be called linear as shown here in the figure. And if there is a pendulum, either it's simple or compound pendulum, then the motion will be angular motion. Now coming to the equation for simple harmonic motion. Let there is a particle and it has mass m, then if it is moving around a point O within a fixed interval and it has a displacement x, then the velocity of this particle can be written as v is equal to dx by dt, and acceleration will be dv by dt, and so it will be d2x by dt square. Now, as from the definition, we learn that the restoring force is proportional to the displacement, and this negative sign is because the force is opposite to the direction of the displacement. So if we put it in a if we put it like equation, then we have to put a proportionality constant k, and this constant is called force constant. From Newton's law, we know already that the force is equal to mass into acceleration. So mass is m and the acceleration is d2x by dt squared. Now these two forces are same, so we can put it together and we will get this equation. Now, solving this equation, we will get a differential equation which is called differential equation for simple harmonic motion. Now, if we want the solution of this differential equation, then we need to integrate this equation and then we will get this kind of equation. Here, the capital A is the constant of integration, and we can get the value of capital A by putting some conditions. Now, because the particle is moving around a fixed point to and fro, so when the particle is at extreme point, that is at x is equal to a, where a is the amplitude, then the velocity of this particle will be 0. So dx by dt will be 0. Now putting the dx by dt is equal to 0 and x is equal to a in this equation, we will get the value of a is equal to omega square a square. Now putting this value of capital A in this equation, then we will get dx by dt is equal to omega under root a square minus x square. Again integrating this equation, we will get the solution of this equation, and then finally we will have this equation which is the solution of the differential equation and is called equation of simple harmonic motion. Here the phi is again the constant of integration and is called as initial phase of the motion. Now coming to the characteristics of the simple harmonic motion, as we already know the equation for simple harmonic motion. Here A is amplitude, phi is phase, time period we can calculate from the known equation 2 pi by omega, where omega is the frequency. As we have already seen the value of omega in the previous slide, so we can get the time period. Also the velocity v is equal to dx by dt, and then we already know the dx by dt from the previous slide, so we can get the velocity. Also the acceleration is dv by dt, so we will get d2x by dt square is equal to minus omega square x, and this is very important thing to remember. Coming to the potential energy, so as we already know that the restoring force F is equal to minus kx, And so there is a well-known relation between force and potential energy for the one dimension, that is F equal to minus du by dx. So putting these two equations together and then integrating it, we will get this equation. So here again, A is constant of integration. Now putting the condition that at the center at x is equal to 0, the potential energy will be 0, because at that point of time there the particle will not be at rest and will have maximum velocity, and thus putting these two values in this equation we will get u equal to half kx square. As we know the value of x, the potential energy will be like this. To get the maximum value of potential energy, we have to put x is equal to a, because at the extreme ends there will be no motion and the potential energy will be maximum. So the maximum potential energy will be half Ka square. Coming to kinetic energy, we know that kinetic energy is equal to half mv square, and as we calculated the velocity already and putting this velocity in this equation, we will get the kinetic energy here, and putting the value of omega, we can get this kinetic energy. Now, as at the center the kinetic energy is maximum, so putting the x is equal to 0 in this equation, we will get the maximum kinetic energy value. Coming to the total energy, the total energy is the sum of the kinetic energy and potential energy. So adding the two values, we will get the total energy. As you can see, the total energy is not the function of x. So it means that total energy do not change with the position of the particle. Now putting the value of k, we can get E equal to half m omega square k square. We can get the total energy in terms of time period and also in terms of the frequency, which is n here. From the graph, you can see that at the center, the potential energy is 0 and the kinetic energy is maximum. As the particle moves towards the end position, that is the maximum displacement, the potential energy increases and reaches to the maximum at maximum displacement, while the kinetic energy becomes 0 and the total energy remains the same throughout the motion. These are the problems which you should solve, and I will provide the answers in the next lecture. So in the next lecture, I will be talking about the simple harmonic motion for simple pendulum and compound pendulum.